Hi everyone, Christian here again to give you another tutorial on MSC Nastran Optimization. Today we're going to go through the process of imposing a design constraint on the failure index if you were working with a composite laminate. So by the end of the video, you'll find that the initial failure index of 22.8 will be constrained so that it does not exceed a value of 0.9. You'll also find out that the layup along with the thickness will vary through our optimization, and we'll eventually hit this new mass, layup, and ply thickness that you see here. This model I've demoed, I've given a longer tutorial before. I recommend referring to this tutorial so you understand more about how this model is constrained. Again, the goal of this video is just to walk you through the process of imposing a design constraint on a failure index for a composite laminate. Our objective is to minimize the mass of this composite laminate. Our design variables are the ply orientations and the ply thicknesses. As for our design constraint, we are going to impose a failure index on each lamina, and there are 8 plies to the laminate, so we are going to impose 8 constraints, one for each failure index of each lamina. Also, each failure index will have a constraint where it has to be less than 0.9. So in effect, there is an upper bound of 0.9 on each failure index. And now let's go ahead and jump to my design model. I've already gone ahead and taken time to build my design model. Here's the original PDF with the cylindrical tube. Here's my design model file. This is already complete with the design variables and the design objective. What I have to do now is replace these constraints with new constraints that I just described. So for that, we're going to use my web app. And this web app is available in the more advanced training I provide for MSC Nastran Solution 200 or Design Optimization. Let me just open a web browser and then we can start looking at the web app. If you do want access to this web app, if you want guidance from me, if you want me to mentor you on a project of your own, my email address is here at the bottom right hand corner. I look at this email address regularly, so definitely send me a message if you are interested. Here we are in the web app. Let's click on constraints, and this is where we are going to go and create our constraints on the failure indices. Once you open the constraints page, it's just a matter of filtering the list for this design constraint available for failure index. So let's go ahead and search for failure. And here one of our results is composite failure criterion. We can select this and it will create a new design constraint in the next table. This is where we go ahead and start filling in our information. For example, our upper bound should be no more than 0.9. We are constraining the first lamina, so we type in a 1 there. And for a failure index, this is where we have to refer to the MSC Nastran Quick Reference Guide. If we look back at our Nastran model, we can see that the cylindrical tube is composed of C-quad elements, so we have to find which item code corresponds to the failure index for this element type. So for this, let me switch over to the MSC Nastran Quick Reference Guide, Chapter 6, Item Codes. We want to look for a section regarding the failure index, so bear with me while I look for that. It's either in the element stress section or the element force section. And here, let's look and find C-quad elements. Those are nonlinear. Here we go. C quad 4 nonlinear. Composite. And here we have stress item codes. And what I could do instead is search for index, and the first result should be, maybe not. Let's look for failure. Here we go. I finally found a section regarding the failure index item code. And just so I remember later on, what section is this in? Oh, right. So this is in the element force item code section. If I look at the C quad 4 element, I see that or rather for item code 5, this corresponds to the failure index. It also says it corresponds to the strength ratio, but here we are purposely working with a design constraint on the failure index, so we can use the 5 here and it would use the failure index FP. If our design constraint was using the strength ratio design constraint, you can still use the number 5 and it would use a corresponding strength ratio value. I'll demonstrate this in a future video, but for now, let's go ahead and use the 5 in this box back in my web app. So I can type in the 5 here. And here, there are a number of ways we can specify which elements this constraint applies to. You can type ELEM here, and you can say this applies to element 1, 2, 3, 4, 5, 6, 7, and every element in the tube essentially. But this tube is constrained in a really convenient fashion. So if we look at the tube from this angle, this tube is constrained in a way at one of the ends where the tube can freely expand in the radial direction. And if we look at the results, the benefit of this is that each ply will have the same failure index for each element. So here, let's go ahead and demonstrate this right now. That's if I had all the other, that's if I had my previous results. Let me see if there's an example here I can demo for you. Alright, so there may be an example here. Let me go ahead and point to this other result file I had ready. So again, the tube is constrained in a way where the tube can expand radially without restriction. The benefit of this is that when we look at the stress results or the failure indices, you find that they are uniform and consistent for each element. So instead of applying this design constraint to each element in the entire model, we can actually just restrict one element, and we have the confidence that since all the results are the same for the other elements, just constraining that one element will be sufficient for this. And just to prove it to you, here I'm going to look at the results right now for failure indices, and here here's the failure index for lamina 8, and here's the failure index for lamina 1, which should be the same. Now let me switch to lamina 6 just to show you further. And here's the failure index for lamina 6. You can see it's 14.2. And again, we don't have to impose a design constraint for each element. We can just select one element, for example, element 64. And if that element is satisfied, then we know the other elements are satisfied too. But if you have to select all of the elements, there's also another method. If you know the property that was used to define the laminate and then assign to all of these elements, for example, the pcomp property type was used to assign the laminate to all of the elements that you see on the screen. Instead of using ELEM, I can type in pcomp and then type in the ID right here. And that'll be sufficient too. And this covers all of the elements. But like I mentioned a moment ago, we want to focus on just one element, specifically element 64. Now here on the right are my new outputs to use in my design model. I'm going to go ahead and copy those and paste those in my design model. And now I can go ahead and perform my optimization. And let's hope that my virtual machine has sufficient memory here. Let me minimize these windows just to look at what's going on in the folder. And right now MSC Nastran is going through the optimization process. Right now, as a kind reminder, if you have any questions regarding this example, I definitely feel welcome to leave a comment below in the comment section. Feel free to email me at my email address. Again, my name is Christian Aparicio. I specialize in size optimization, whether it's composites, area elasticity, and various other analysis types MSC Nastran can perform. I also include access to the web app if you opt in for any advanced training, any mentoring, any guidance, and so on and so on. So our analysis is complete. We're now going to look at the results in the F06 file. The reason I'm doing this, I just want to take a look at the very bottom of the F06 file and make sure that it says the message run terminated due to hard convergence. And so here I see the successful message indicating the optimization went through successfully. Now let me go ahead and look at the objective. So we started at a mass of, let me see what units I was working on. So we started off with the mass of 1.59 slinches. And then if I trace these values all the way down to design cycle 25, we ended up at a value of 0.223 slinches. You can see here there's a slight variation in my results that I was expecting. But let's just attach these new results to my Patron database just to make sure that the optimization went through successfully and every ply has a failure index of less than 0.9. So here let's go ahead and point Patron to that result file. And let's click on this OP2. And then before that, I should definitely remove some of these old result files. And let me go through that process again. One thing I want to point out, my PowerPoint has different results. According to this optimization we just ran, the new mass is 0.223 slinches. I was expecting a new mass of 0.34 slinches, which is okay. The one thing I want to confirm right now is that the failure indices are below 0.9, and right now we're going through the process of attaching these results to Patron. So let's go ahead and inspect what we have now. So here in this plot I'm making right now is the failure index for the initial design. You can see this is the failure index for ply 8. Ply 5 has this failure index of 14.2. But if I just want to know what the maximum failure index for each ply, I can select all the plies here, leave the option as maximum, and then Patron will go ahead and display the maximum failure index for all 8 plies. And here we see that the maximum failure index for the initial design is 21. Here in the second set of results is the final design or the optimized model results. And here let's plot what the failure index is for that. And here I see that my failure index is actually 2.62, which is not correct. Again, we needed to make the failure index no more than 0.9. So let's go ahead and see if we can find out what happened here. Oh, right. I just constrained lamina 1. Hence, we have one row here. What I needed to do is make a constraint for lamina 2, 3, 4, 5, 6, 7, and lamina 8. That's what I neglected to do, and I can take time right now to update these results. But first, let me go back to Patron. Let me go ahead and unattach my old results. And the reason I'm doing this is because we just essentially need to erase all of the old MSC Nastran files produced during the optimization and recreate new ones. So let's go ahead and delete all of these except for this PDF file. And let's go ahead and update this table. Again, we're doing this for just one element. And we're doing this because the way the model is constrained allows us to just focus on one element, since the results for one element are the same for the other elements. We're going to use the same upper bound for all of the other laminas. We're going to use the same item code for all of the other ones too. So item code 5. And then for the lamina number, this first row is for lamina 1, but then we need to constrain lamina 2, 3, 4, so on and so on. And now this is complete. I've constrained all 8 laminas. So now what I can do is copy all of these new design model results. And I can replace my old constraints that I created. And now I can perform the optimization again. And this time I should see that each ply is under the constraint. Alright, now that my analysis is complete, let's go ahead and look at the F06 file. Like before, we want to make sure that it says run terminated due to hard convergence at an optimum. And here we see that we successfully completed the optimization. Let's look at the objective values. We went from a mass of 1.59 slinches to a mass of 0.3383 slinches. And this corresponds to what I originally planned to have. So perfect. So now we can go ahead and discuss our results. So here on the left is our original layup. We had plies in the 85 and 60 degree section or directions. Our thickness of the plies was originally 0.010 inches, but now our ply thickness is 0.002 inches. Our failure index before was at a maximum of 22.8, and this was for lamina 8, and I believe the other 85 degree plies. But now our failure index is below 0.9. Here is just to summarize what the progression of the design variables were, specifically the ply orientations. You can see for the first about 11 or first 10 design cycles, the optimizer really didn't modify the 85 degree ply. It wasn't until design cycle 10 that the 85 degree ply finally was decreased, whereas the 60 degree ply was immediately modified in design cycle 1 and 2. Let's go ahead and see what happened to the thickness. The thickness after design cycle 1 was immediately modified. I suspect that the failure index was in violation, so then the thickness had to go up again to satisfy the constraint. But then again, it dropped after design cycle 11. And here is a plot of the normalized constraint history. Again, each design cycle will have a different constraint that's governing the design. In one design cycle, the maximum normalized constraint might be to ply number 1 as an example. The next design cycle, it might be that ply 4 is now violating the failure index constraint. So then that governs the design cycle for that one. And each design cycle after that might vary from constraint to constraint. But by the end of the optimization, that's where you have all of the constraints are satisfied. So now let's go ahead and look at my results in Patran just to make sure we have what we intended to have. So like before, I'll go ahead and select this new OP2 file. That's a result of the optimization. This optimization result file has results for the initial design, and it has the results for my final design. So I can view the failure indices of the before and the after. And that's what I'm working on right now. As soon as I attach these results in Patran. And now I've gone ahead and attached my results to Patran so we can go on and review our failure indices. And here, just as a reminder, if you look at the first row, it's very small, but it says D as in Delano and then 0 as the number 0. This indicates the initial design, and D10 is our final design. So let's go ahead and plot our failure index for the new design, if you will. And you can see the failure index is 0.9. And now what about the other plies? Let's go ahead and select all the plies and view which one has the maximum failure index. Perfect. So now our failure index for all the plies is less than 0.90 or less than 0.9. You can see here the failure index for one of the plies is 0.903. That's a tolerance. If you wanted to, you can modify that tolerance so it's exactly 0.9000. But here there's some flexibility in the tolerance, so you're going to have a small access violation of the design constraint. So now let's see, I'm close to the end of the video, so I guess let me make my last few comments. In the next few videos, I'm going to cover how to impose constraints on strength ratio, stresses for the ply, so if you're dealing with stresses in the 1 or 2 direction. I'm also going to walk you through the process of incorporating design constraints if you were working with strains in the 1 and 2 directions. So definitely watch out for those videos. And as always, if you want more advanced training, you want me to mentor you, if you want me to guide you on an optimization example of your own, if you want access to the web app that allows you to rapidly generate your inputs for MSC Nastran Optimization, you can email me at this email address here and I'll definitely get back to you. Thank you for watching.